Hi, my name is Ricardo Ruiz, ID A01383658, and this is my final challenge. So basically for this challenge, we're applying a CTC on a double link manipulator. A CTC is a computer torque controller. And well, basically here we're applying these equations that you see in the screen for making our controller. Basically, the system will be governed by these nonlinear dynamic equations based on Euler-Lagrange. So basically, we will have that QR dot, and QR double dot, each one representing position, velocity, and acceleration. We will have E and E dot for tracking the errors. And we have these equations for representing the mass inertia, the centrifugal effects, and the gravity. So basically, knowing this, we will be developing this in our Python code. So in here, we have that, it shows basically how it will be structured. We will be subscribing to the topic joint states to get the actual joint positions and velocities. And we will compute the track of the errors by applying the CTC law to calculate the torques in U1 and U2. So this will be published inside the DLM input topic to actuate the joints. And well, it will run at 200 hertz. And well, basically, why are we using the CTC versus the PID? So basically, CTC offers more advantages over PID. PID doesn't account for the system's non-linearities, and this often results in slower or less accurate tracking by the PID. And in the other hand, here in the CTC, we use an actual dynamic model to represent the effects, which give us a more smoother, a faster, and robust control. Also, another disadvantage of the PID will be that um, if the sensors have a lot of noise, it will not be able to do the trajectory right. But well, in this case, since we're using the CTC, we won't see any of those problems, and the graph will be smooth. So now let me show you my ROS. So basically, here is my code. Firstly, we're introducing the same libraries as always. We will have the filter to multi-array, which we also use in a single link manipulator. We have our callback and our stop functions. And then here we will have our given variables. So basically, we'll have one for each link, the masses of the links, the lengths, and the offsets that each one of them will have. For the controller, we'll be using a KP, initial KP of 10 and the KD of 4. And well, here is the code for applying the equations. As you can see, firstly, we're getting our QR, Q dot, and Q double dot in the form of this matrix. But basically, it's just getting the sines and the cosines of each one of them and placing them where they belong. And then here are the equations I showed in the previous slides. And basically after this, it will just get the tau and publish the message inside the U. So basically, this will be the code. We're just getting the solving the equations with the values given, and we're publishing inside this one, U, which U is given by U data, and U data is given by the float of the tau. So it's all interconnected. So now let me show you the code. So as you can see here, this will be how the movement works. And basically, if we were to change KP or KD, I will show you in a little bit, but after I myself controlled changed the variables. After testing, I saw that if KP is increased, it makes the system respond faster, and well, it will track the desired location more aggressively. But if you put it too high, it will cause an instability, and at one point it won't even move because the simulation won't do it. And on the other hand, if we increase the KD, this will help us dampen the motion and reduce the oscillations that it will have. But also, if you have too much, it can slow down by far the system, and also it won't start. So I will show you in a little bit one example of this. But well, here we have from with a KD of 10 and a KP of 10 and KD of 4. So now let me show you what will happen if we change, for example, the KD to a very high value. And since I mentioned before, it will dampen the system, so it will go very slow, and well, it won't even move. Yeah. You can see it won't even work. Well, thank you very much. This was my final challenge.